understand why people hate probability. It's so great. It's the quantification of uncertainty, which sounds like such a poetic word, but it's really just, I don't know. I'm excited about probability. I love probability. This is when I nerd out. You should also talk to Daniel Gatien because he also teaches statistics, and I cannot imagine him being as excited. Like if he were as excited as I am right now, he'd probably be jumping around or something like that. All right, so the first question is, why do we use probability? Okay, so why probability? Why do we have to care about probability now if we're doing statistics? What's the point? So why probability? Yes, I know you had him for Cal 1. We report to one another. Oh, that's not true. Okay, so we're going to try to think about problems that you've seen before. You've already done a lot of work in this class with respect to different types of studies, and we're going to try to see why probability comes into play into any of those. So the first thing is I want to refer to the yawn experiment. Yawn experiment. Remember? So this is the experiment that you saw the video for. So the Mythbusters clip that you had to see for homework 2, and the Mythbusters basically said, okay, we're going to compare two given populations. One of those populations is going to be exposed to a treatment, which is yawning before entering the room, and the other is going to be a control, which is not going to be exposed to the yawn. And then they said, of the team that had no yawn, 25% ended up yawning, and then of the group that had been exposed to the yawn, there was 29% of them that were exposed to yawning. Right? And one of the questions that I asked you was, is this a big enough difference? So is this a big enough difference to conclude that yawns are contagious, that yawning is contagious. I also feel like yawning right now. And you know it must be the use of the word because it's not that I'm bored by probability. I already told you I love probability. Okay, so this is the first question. Is it enough to see this difference of 25 versus 29 to conclude that yawning is contagious? This is a question that I had asked you to answer. Then there was another example that we saw in class, which was the polio vaccine trial. In which we saw that the proportion of contagions was different between the vaccinated group and the placebo group. And then again, the question is the difference in proportions big enough to conclude that the vaccine is effective?
Sorry, with the equal sign with the bar, it's for the word difference?
Yes.
Okay.
So is the difference in proportions big enough to conclude that the vaccine is effective? That was another question. And then this is just like a greatest hits of the semester so far. You also had an example with hybrid cars versus gasoline cars, right? So in that example, the question is the difference in the distributions large enough to conclude that electric cars, that hybrid cars are more efficient, more fuel efficient. Right? So in all of these examples, there was this kind of lingering thought at the back where we were like, well, it looks kind of different, but is it different enough? Is this really different enough for me to say that there's something there? Right? The idea that we're going to use in this class is we're going to try to then quantify some things through probability in order to answer that question. Is it enough? Right? Because in all of these statements, you have so what I'm asking here is first, is it a big enough difference? Is the difference in proportions big enough? Or is the difference in the distributions large enough? Right? So what does it mean for a difference to be large enough? What is a significant difference? How can I conclude from a specific difference between the two distributions that there is actually something there? And the kind of parallel question that comes with this is, or so I could complete each one of these sentences by adding the following. Or are our observations reasonably explained by chance alone? Right? Is the difference big enough, or are the observations reasonably explained by chance alone? Are the distributions different enough, or could these differences be reasonably explained by chance alone? Are the difference in proportions for the vaccine trial big enough, or could they just be explained by chance? Right? So that's the alternative question that we're asking. Is it possible that it could just be explained by chance? Can I please see a show of hands for everybody that understands this kind of logical argument? Very good. Okay. So the question here is, for example, to determine whether the difference between 25% versus 29% is large enough, especially considering that this came from a sample of size 50, right? Because the thing is, whenever you conduct any experiment in real life, whenever you do anything in real life, you can expect some variation. You can expect some variability. So, for example, you could expect you could expect that somebody will yawn or will not yawn, and that doesn't necessarily have to do with the fact that they were exposed to the yawn or not, right? So we have the controlled variability, which is our treatment, and then we have the other side, which is the variability that we cannot expect, right? And because of that variability, we need to have some way of accounting for what kind of effect we should expect from random chance, and how do I differentiate that effect from random chance from the effect of something else, for example, a treatment, a vaccine, or the difference between two types of cars. Okay, can I see a show of hands for everybody that understands that?
Question?
Yep.
Like, it's not super important, but why did you choose that Mythbusters video?
Because um, the experimental design is very clear. Yeah, it's just very easy. So they have an experimental design that is very clear, and they provide the statistics that they compute, so the percentages that they compute, as well as the sample size, which means that we will actually be able to answer the question of whether the results were significant or not by the end of the semester. So we can use all the information. All right, so then here's the thing. Variation can occur By chance. By chance. The goal, so our goal is to determine whether the difference between two given proportions or two given distributions could be attributed to something other than chance. So goal is to I looked for examples and I found Mythbusters. I am not I tried to watch the series. I think I recommended it at some point. 100 Humans, which is on Netflix. Um, I tried to watch a couple of the examples, and they have some that are actually useful, but they don't always provide all the information, and so it's a little bit more difficult to interpret. Yeah, so like they don't necessarily say how they assign something to a given group, or maybe if they give mean, they don't give the standard deviation, and then like because of that missing information, it's not complete, it's not a full story, and therefore I can't use it exactly in order to analyze it in class. Although maybe we'll be able to find some. If you have some experiments that are interesting to you in 100 humans, we could try to analyze them. You can send me a message and I'll try to figure out how to include it in class. All right, so goal is to determine whether an observed difference is plausibly explained by chance, or if not, whether it should be attributed to something else. Now, something else, of course, depends on the context. So in the context of the Mythbusters thing, and the something else is whether somebody is exposed to a yawn or not. In the polio vaccine example, something else means whether somebody is vaccinated or not. And in the car example, the something else should be the type of car, right? So that's the idea here. Now, of course, if we want to quantify whether something can be plausibly explained by chance alone, we need to understand what is likely, what is possible, what is plausible, and therefore we need to understand probability, right? So probability allows me to quantify phenomena, the likelihood of phenomena, and so by understanding probability, I can try to assign a value, a certain level of uncertainty to any result that I observe, and from that I can determine whether that was a likely outcome or an unlikely outcome, right? So the answer lies in probability. Okay, so I decided for this part, there's a bunch of definitions that we're going to have to use, but I thought it would be a lot easier to understand if we understand the definitions based on an example. So we're going to work in parallel. So I'm just going to make a table of definitions so that you have it, and it's going to be like a good aide-mémoire. Okay, so it's just a way of remembering it. So I'll start with just the table over here. I'm going to do one column for the definitions and then two columns for two different examples that I'm going to work on. So this is the definition.
Yeah, how much space is this going to take up? Like, do I start a new page or do I keep going
It's
on?
going to be, so I write pretty large. It takes about 2/3 of my page.
Okay.
Yeah. So a definition. And then I'm going to do two examples. So example 1 and example 2. Okay, so that way we can get right ahead and and understand the definitions in a specific context right away. Okay. We're going to start with the definition of the definition in the context of probability of an experiment. So we've talked about experiment in the terms of experimental design. Now we're going to talk about an experiment in the probability context. It's just vocabulary. This is the way that we need to do things. So just make sure that you understand that difference. Okay, so we have an experiment in probability is the process by which an observation or measurement is obtained. Okay, so this means that an experiment is the setup of something that will give a probability. So we're going to look at two experiments in parallel so that we can look at all of the other definitions in those two different contexts. The first experiment is a classic probability experiment, which is drawing a single card from a shuffled deck. Okay, so drawing a card from a shuffled deck oops. And the second example, again, can be any process by which a measurement or an observation is drawn. So the second example here is going to be measuring daily rainfall. Right? These are two experiments. The next definition that I'm going to give is that of a simple event. So a simple event is the outcome observed on a single repetition of the experiment. For example, in the experiment of drawing a card from a shuffled deck, a simple event could be getting the ace of hearts, getting the seven of spades, getting the nine of diamonds, and so on. Okay. And in the second experiment, measuring daily rainfall, one possible outcome could be, I don't know, a fall of 2.6 millimeters or 3 centimeters or 0 millimeters and so on. All right, so so far so good, I think. The next thing is an event is a collection of simple events. And what's important to note here is that an event is a set. Okay, so the set can be sometimes expressed as an expression, or it could actually be expressed as a list of outcomes. In whichever case, when we refer to an event, that corresponds to a set. So that means, for example, in the context of drawing a card, an event could be drawing a heart, which is expressed as, again, it's written as an expression, but what it actually means is the set that contains all the possible outcomes that are hearts, right? So that means the ace of hearts, the two of hearts, the three of hearts, and so on until I get the king of hearts, right? So these are all the possible outcomes that are included in the event drawing a heart. In terms of the rainfall, you could say, for example, it rains more than 1 centimeter. Right? So that's one possible event, which would be the set of all possible outcomes. For example, here, all possible outcomes or values, such that those values are larger than 1 centimeter. Right? So this is the set. Could I please see a show of hands for everybody that is following so far?
Okay, I have a question for how you wrote the second set.
Mhm.
Is it like x semicolon? X is greater than 1?
Yes,
Okay.
semicolon, which means such that.
Yes.
Yep,
Does it mean like a event is like the probability of which it happen?
not yet. No,
No.
so the event
Okay.
is the fact of it happening, and then we're going to quantify the probability of
Okay.
events.
Okay.
All right, so here we go. Next definition is going to be that of mutually exclusive events. So two events A and B are mutually exclusive if when one event occurs, the other can't occur. The other cannot, and vice versa. Okay, so mutually exclusive is the thing that we're defining here. So, an example of two mutually exclusive events would, for example, be drawing a 7 and drawing a card with an even number. Or in the second type of event that we have here, we could have that one of the events is there being no rain, and the other event would be it rains between 2 and 10 centimeters. Could I please see a show of hands for everybody that understands this?
Can you explain it more?
Yeah, sure. So two events are said to be mutually exclusive if they can't possibly happen at the same time. So that means, for example, here, drawing a 7. Well, if I draw a 7, then I know I didn't draw a card with an even number. And then if I draw a card with an even number, then I know that I did not draw a 7. Right? In the same way, if I know that there is no rain, then that means that I know that it didn't rain between 2 and 10 centimeters. And if I know that it rained between 2 and 10 centimeters, I know that there wasn't no rain. Does that make sense?
Yeah.
Okay. Good. All right. So that's the fourth definition that we have here. And the last one in our table is going to be the set of all possible events. The set of all possible events is called the sample space. And it's denoted by what?
Like when you speak and you say there wasn't no rain, like
Uh-huh.
that means there was no rain. Not like there wasn't no rain. It's like
No,
there
it
wasn't
means
no rain.
depends on whether you're being grammatically correct or incorrect.
It matters. It depends on who you're
Depends
speaking
on
to.
the tone. Yes.
There wasn't no rain.
There wasn't no rain. That's how I mean
There wasn't no rain.
it.
Okay, I have a question for the symbol. Like, how is this like a treble clef? Like how I don't know. Like, how do we draw it really? Like, what is it?
Yes. It's an S. It's a calligraphy S, and you can be as fancy with it as you want.
Okay, so as long as it's like a capital cursive S, it's good. Okay.
I write it like that, but up to you. I'm curious to see your fancy S's. So might as well start practicing your calligraphy. See how it goes in your probability assignment. Okay, so for example, in terms of the card draw, the sample space, so the sample space is going to be all the possibilities for a draw, which means the sample space here is going to be every possibility starting at the A of clubs, then the 2 of clubs, and so on until you get to basically going through all the possible values until you get to the K, the king of diamonds. Right, so then there are 52 possibilities. Teaching probability, I've realized that I started playing cards very young, so I just want to know who is familiar with the composition of a deck of cards. Could you please raise your hand so that I can make sure that I'm speaking on known terms? All right, so 4 suits of 13 cards. That's 4 times 13, which is 52. And I'll be using this example quite a bit. But we can see. Let me see. Do I play poker? I'm not very good at poker. I don't have a very good poker face. So then for the second type of, for the second possibility here, we have that the sample space is going to be equal to the set that starts at 0. And here we're going to say that it ends at infinity. Now, of course, it's not going to end at infinity. Okay, you cannot have billions and billions of millimeters of rainfall. But because we don't know what the maximum of this set is going to be, we're just going to set it at plus infinity. And in that way, we know we're guaranteed that the set that actually corresponds to the sample space is going to be included within this one. Okay, so this is the most information that we have because we don't know what the maximum is going to be. Can I please see a show of hands for everybody that understands?
Miss,
Yeah.
I got a question. So, like, what's the difference between the event and the sample space? Like, can't you say like drawing a heart is like the sample space of all the cards with hearts? Like, can't you say that?
So drawing a heart is a subset of the sample space. The sample space, it contains
Okay.
absolutely all of the possibilities, and every
Okay.
event contains some of the possibilities, which means that any event is going to be a subset of the sample space, but the
Okay.
sample space is the one that's going to contain everything.
Like everything.
Everything.
Okay. Okay. Thank you.
Yeah. Can I please see a show of hands for everyone that's okay with this? Okay. So in order to put these definitions to use, we're going to do the following example. I want you to try to answer it as much as you can. So we're going to have example. Yeah. So a student, whoops. Takes 3 tests during a given semester. This example actually hit home a little bit closer last year because my students were actually taking 3 tests, which means it's a little bit more relevant then. But she either passes or fails each of the exams, right? So she either passes which I'm going to denote with the letter P, or fails each exam. Each test, sorry. Test. It's going to be 5 questions. The first question that I want to ask here is to list all the possible simple events. Okay, so that's the first thing. You're going to have to list all of the individual outcomes that are possible. Instead of asking for each one of you to come up with all of the answers and contribute them, I want to ask you to write them in the chat in a way that you think would make sense. You can write them one at a time. So for example, what is one possible outcome? What is one possible simple event? There you go. PPP. Right? Which means passes, passes, passes. Everyone here is being very positive. I like it. The next one is fails, fails, passes, fails, fails, fails. Some pessimists in the house. All right. I think I saw fails the last test, which is, I'm guessing pass, pass, fail. So here we go. We have P, 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 or maybe she will pass the first two and then the last one she will fail, or maybe she will pass the first, fail the second, and then pass the third, or maybe she will fail the first and then realize that she needs to study more and pass the next two. But the possibility is to fail the first two and then pass, to fail the first and the third and pass the second, or to pass the first and fail the last two, and finally to fail all three of them. Right? These are all the possibilities that we have. That means that our sample space is just the set that contains all of these possibilities. All right, so now I'm going to write a given event. So I'm going to write A here, then I'm going to write, oops, for 3, I'm going to write B, and I think I have C. So 4 to C. Now what I would like you to do is in the chat, write the set that corresponds to the event that I describe. Okay, so that means write the set, the list of possible outcomes that correspond to the event that I'm describing in each of these problems. So for A, I have that the event is she fails at least 2 exams. At least 2 exams.
Okay, I have a question.
Yep.
About this. Sorry, I'm kind of slow. So wait, are we just doing the same thing we did for number 1, just like within the constraints of what you're saying?
Exactly.
Okay.
Just listing the outcomes that corresponds to this set. Fancy, almost. Yes, you also have to include for the possibility that she will just fail them all because it's at least, and therefore it's either 2 or 3, right? So that means this set is going to be equal to pass, fail, fail, or fail, pass, fail, or fail, fail, pass, and then fail, fail, fail. All right, then the next event is, I lost my notes. She gets different results in the first and second test. So I'm looking in the chat. What are the possibilities? Yes. Okay, so I'm seeing it. The first possibility, she passes the first one, and so she has to fail the second one within the constraints of this event, and then she can either pass the third or fail the third. So it would be pass, fail, pass, or pass, fail, fail. Or she can start by failing and then fail, pass, pass, or fail, pass, fail. Okay. For C, you have give an example of C. Oh, sorry. This is an example. Give an example of an event C containing two simple events. Okay, and what I would like you to do is to describe this event, not write it as a list, but try to describe it. So what's a description of an event that would contain two simple events?
Wait, wouldn't just saying that she like did the two tests means that they're two simple events? Like within it automatically?
I'm not sure what you mean.
Like, okay, is the question that we need to like make an example of where only two events are possible?
Two
Like it
outcomes,
can't
so
be a
two
minimum
simple
of two.
events.
We need to like make
It,
it exactly. Okay.
it needs to be exactly, yeah. So in this case, I want an event that contains exactly two outcomes. Yes, that's the one I was thinking about. She gets the same grade on all tests, right? So she either passes them all or fails them all. So Rita, there's three outcomes in that one because you can always tie, but also this is within the same context that we have in the class. So we will leave those for more original times. In this case, the constraints were pretty pretty tight. So we'll have that she gets the same grade. In all the tests.
Wait. Okay, I'm I'm still a bit confused. If she gets the same grade, doesn't that mean that like there's like three events or like there?
Oh, I see the difference. Okay. One simple event is one outcome for the three tests because the experiment here is not each test, it's the set of the three tests. So then the two simple events here would be fail, 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 or pass, pass, pass.
I have a question. It's just, but one of the options in the simple events was FFF or PPP. So how can it be more than one simple event as the same thing?
So you can think of the simple events as the individual outcomes and an event as a collection of simple events, right? So that means that here, what I'm asking is to come up with one event or one collection that only contains two simple events or two items, okay? So those two items here are going to be fail, 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 which is one of the items that is in the sample space, and pass, 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 which is the second one of the outcomes that is in the sample space. Does that answer the question?
Yeah. So like number 2 and 3, they were also examples of events.
Exactly. So these are events because they're a collection of outcomes, right? Which is why I've been using curly brackets in each of these because they are sets, right? So they're possible sets of outcomes, right? So that's the important part, to realize that an expression can also be translated as a set. Okay, Vishaka, was your confusion cleared up?
A bit.
A bit? Okay, maybe with another example it will get a little bit better. So the next question that I want to ask is to give an example of two mutually exclusive events, E and F. Okay, so you need to give an expression for E and an expression for F.
I have a question for number
Sure.
4. Because I'm still not sure if I totally understand the question. So, for example, if we were to give another example for number 4, would number 2 or 3 fall in this category?
Number 2 or 3 cannot fall in this category because each one of these has 4 simple events, right? So 1, 2, 3, and 4. And so they are not events that contain only 2 simple events.
Okay, so we need to find like a statement that the only possible outcomes is two pairs, kind of.
Things. Yeah, 2 things.
Could you give like another example for number 4 just so like I understand, please?
Sure. Another example for number 4 would be she passes the first 2 tests. Right? Because if I have this, then she will either pass, and then fail, or she will pass, and then pass. Does that make sense? So you use S, I'm not sure. Okay, so I'm answering questions one at a time. For Rita, E and F are just the names that I'm giving to the events in problem number 5. So you need to find one event E and one event F so that E and F are mutually exclusive so that they can't happen at the same time. And Sarah, I'm confused about your question.
Sorry for all my questions.
No, this is great.
For like when we write our like our sets, our curly bracket things, are we using the cursive capital S in these cases?
So each one of these is a set that corresponds to the event, right? So these are all like that. So the events are also sets, right? It's just that the elements of each event must come out of the sample space. So you have basically like a sample space, which is like a bag of possibilities, right? And then in each event is one way that you have picked from the possibilities in the sample space.
That makes sense.
Okay, good.
Thank you for the diagram.
All right, good. Does anybody have an idea for 5? 2 mutually exclusive events. Passing at least 2 tests and failing at least 2 tests, or passing all tests and passes 2 tests and fails 1 test. That's exactly right. Essentially, what we're looking for here is a contradiction, right? 2 things that could not possibly happen at the same time, which means that I'm going to go with, yeah, both of them. So passes at least 2 tests. This is one possibility, and then fails at least 2 tests, right? And these 2 cannot happen. If you were to list, oh, I see. F over here doesn't make sense. So this was a poor choice of letters. I'm gonna call this E, and I'm gonna change the F for D so that we don't have F for fails and also F for the event, because then that's gonna get confusing. So for passes at least 2 tests, we know that this is either pass, 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 fail, fail, pass, or fail, pass, pass. And then for for passes fails at least 2 tests, this is either fail, 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 pass, fail, fail, pass, or pass, fail, fail. And what you can see is that there is no overlap in the simple events. Right? So there are no simple events, no items, no possible outcomes that are in both E and D. Okay. So for Friday you have homework number 4, which means I'm not going to add to that right now. We're going to start talking about set operations, which means how do we combine sets. But if you want to practice this on your own, I would suggest that you try to think about any kind of random process that you can think of. So you could think about the classics, coin flips, rolling a die, or picking a card. That's like the usual things to get intuition about. And you can try to define events with the same constraints as here. So you can try to find events that contain only 2 simple events or a fixed amount that you set up, or events that contain mutually exclusive events. And that way you'll be thinking ahead, and hopefully it will be easier to understand once we get to Friday's lecture. Do I have any questions? Everyone okay? All right, so then I'll see you Friday or later today if you have questions about RStudio. Have a nice day.